Hi, today we are going to see orthogonal properties of the Legendre's polynomials. Orthogonality of Legendre polynomial, we are going to see here the orthogonal property or orthogonality of the Legendre polynomials. The property is this integral minus 1 to plus 1 pm of x pn of x dx that is equal to 0 for m not equal to n. Okay, so this is the orthogonality property that we are going to prove. Along with this, we are going to see the integral minus 1 to plus 1 pnx square dx. It is equal to 2 over 2 by 2n plus 1. So this is also we are going to see, and we will be combining these two equations. We will be combining this equation and writing it as a single equation. So this is what we are going to do. For proving this, we start from this Legendre equation. This is our Legendre equation. We have been studying about the properties, various properties of the Legendre equation. This is the Legendre equation we know. So 1 minus x square d square y by dx square minus 2x dy by dx plus n into n plus 1 y. So this can be written as d by dx of 1 minus x square dy by dx. d by dx of 1 minus x square dy by dx. So as you take the product rule, we will get this as d by dx of, as we differentiate it, you will get these two terms. So these two terms can be written like this. Okay, d by dx of 1 minus x square dy by dx. So you will get 1 minus x square d square y by dx square, and then you keep dy by dx here and differentiate this 1 minus x square, so you will get minus 2x. Okay, so it is possible to write the Legendre differential equation in this fashion, and we will later on see that this is because the Legendre equation is self-adjoint. Okay, we will learn more about it later on. So let's continue. So d by dx of 1 minus x square dy by dx plus n into n plus 1 y equal to 0. And we know the solution of this is y equal to pn of x. Okay, because here we have n. And if we are taking pm of x, okay, pm of x will be solution of this equation. If we take indices as m into m plus 1 pm, then pm of x will be the solution. So here you can write y as equal to pn of x, and here you can write y as equal to pm of x. Okay, so that's why you are writing it like this. Here we have taken pn, and here pm. Here you are taking dpm by dx, here dpn by dx, here dpm by dx. Okay, so you are taking y as pn of x here and y as pm of x here. Okay, so we have this two equations, and what we do is we multiply equation 2. Okay, equation 2 is multiplied by what? Pm of x. Okay, we are multiplying equation 2 by Pm of x, and this is multiplied by Pn of x. Okay, multiplying by Pn of x. So what we get? See, we will be getting this. Okay, and then we subtract. It's subtracting. We are multiplying first equation by Pm and second equation by Pn, and then we subtract. So you will be getting this. Okay, so as you subtract, you will get, this is the first term, subtract, and second term, it will be this. Okay, now once we have this equation with us, we integrate this. We integrate the entire equation between the limits -1 to +1. Okay, so we are integrating. So as we integrate, we will get this integral -1 to +1 Pm. Similarly, integral -1 to +1 Pn d by dx of this. Then we are writing this as n minus m into n plus m plus 1. Okay, so you have this n square minus m square plus n minus m. Okay, here what we have is see, n square plus n. Here we have n square plus n, and here m square plus m. So that can be written in this fashion: n minus m into n plus m plus 1. So you will be getting n square minus m square here, then n minus m. Okay, then minus integral -1 to +1 Pm dx, that is equal to 0. Now we are integrating this by parts, integrating these two equations. Integration by parts, because we have here Pm and d by dx of 1 minus x square dpn by dx. Here Pn d by dx of 1 minus x square dpm by dx. Okay, so as we do is the integration by parts, we get Pm as Pm 1 minus x square dpn by dx integral the limits -1 to +1, and then integral -1 to +1 1 minus x square dpn by dx dpm by dx. Okay, we are doing integration by parts. So one function is 1 minus x square dpn by dx, the other one is Pm. So here same way, here you can you have this minus Pn 1 minus x square dpn by dx limits -1 to +1, and integral -1 to +1 1 minus x square dpm by dx differential of, or first order differential of Pn with respect to x dpn by dx. We are doing the integration by parts. See here, if you apply the limits +1 -1 for x, this will be 0. Okay, here also if you apply the limits, this will be 0. Okay, and this will get cancelled. See, dpn by dx here, similarly dpm by dx here. So this will get cancelled. Okay, so all these terms will get cancelled. These two will get cancelled, and this one is 0, this one is also 0. Okay, so we are left with this integration only. We are left with only this integration. Okay, so that is written here. N minus m into n plus m plus 1 integral minus 1 to plus 1 pn x pm of x dx, that is equal to 0. So here if n is not equal to m, if this is not equal, then the rest of these terms has to be 0, but this one is not non-zero. If n is not equal to m, this will not be 0. Okay, so we have this integral minus 1 to plus 1 pn of x pm of x dx, that is equal to 0. So the first part is solved. Actually the orthogonality is solved. The Legendre functions are orthogonal. So that is solved here. In the next step, we have to prove that this one, integral minus 1 to plus 1 pn x square dx, that is equal to 2 by 2n plus 1. Okay, integral minus 1 to plus 1 pn x square dx, that is equal to 2 by 2n plus 1. So from the generating function we prove this. You know, this is the generating function. 1 minus 2xz plus z square to the power minus of is this. We square on both sides. Okay, we square with the square of this. So here we have to square, here also you have to square. So on the left hand side, as you square, you will be getting this. Okay, 1 minus 2xz plus z square to the power minus 1. Here I am taking sigma m equal to 0 to infinity z raised to m pm of x. Sigma n equal to 0 to infinity z raised to n pn of x. Okay, this way you can write. Here on the right hand side, you have to take the square of this. So we are writing it like this. Summation variable m equals 0 to infinity z raised to m pm of x. Here summation variable n equals 0 to infinity z raised to n pn of x. And as we take the product, you will be getting what? The z raised to sigma m equal to 0 to infinity, sigma n equal to 0 to infinity, z raised to m, z raised to n, pm of x, pn of x. This is sigma n equal to 0 to infinity, z raised to 2n pn of x square plus sigma m equal to 0 to infinity, sigma n equal to 0 to infinity, m not equal to n. So actually here m has to vary from 0 to infinity. N has to vary from 0 to infinity. What we do is, during this variation, there will be certain values for which m is equal to n. Okay, m equal to n. That is written here. Okay, set m, when m equal to n, these two indices will be equal. So you have pn x square, z raised to 2n, m equal to n, and sigma n equal to 0 to infinity. So we are here taking all terms which have m equal to n. And here we have sigma m equal to 0 to infinity, sigma n equal to 0 to infinity, m not equal to n. That is separately written, z raised to m plus n, pm of x, pn of x, dx. Now what we do is we integrate this between, with respect to x, between the limits minus 1 to plus 1. So here you get integral minus 1 to plus 1, 1 minus 2xz plus z square to the power minus 1 dx. Here on the right hand side, you have the two terms, integral minus 1 to plus 1, okay, plus 1 z raised to n pnx square dx plus sigma m equals 0 to infinity. This integral z raised to m plus n pn of x pm of x dx. Okay. Here this term will be 0 because here we have m not equal to n, and here we have integral minus 1 to plus 1 pn of x pm of x dx, that is equal to 0. The first part of the proof, okay, z raised to m plus n can be taken outside the integral. So this term will be 0 because of the orthogonality relation. Okay, so we need to consider this term and this term only. Okay, this is 0 because of the orthogonality relation. Okay, so we are left with this integral. So here, as we integrate with respect to x, I will be getting log 1 minus 2xz plus z square by minus 1 by 2z. Okay, we are integrating with respect to x. X is present here. So as I integrate, I will have log 1 minus 2xz plus z square here, and this minus 2z. Okay, here you have this minus 2z that comes outside. So minus 1 by 2z. Okay, so this is the integral of this part. Okay, and here we have this sigma n equals 0 to infinity z raised to 2n integral minus 1 to plus 1 pnx square dx. Okay. Now here we apply the limits. Here we have lower limit minus 1. Okay, lower limit minus 1, upper limit plus 1, we apply the limits. So here you have to remember that you are applying this plus 1 or minus 1 to x, not to z. So you have as you put plus 1, you will have log 1 minus z square here, and as you put minus 1, you have log 1 plus z square here. Okay, and you are writing this as the log 1 plus z square. Here you have a negative sign. Okay, here you have a negative sign here. So the log 1 plus z will come here, log 1 minus z will go here. Okay, and this 2 here, that will combine with this 2. Okay, that will combine with this 2, and we have this expression. Now we expand this log 1 plus z and log 1 minus z. Okay, we know the expansion of log 1 plus z. It is this z minus z square by 2 plus z cube by 3. Log 1 minus z is minus z square by 2 minus z cube by 3, like this. Okay, so the even terms will cancel. Minus z square by 2, then minus plus z square by 2, that will cancel. Minus z raised to 4 by 4, that will cancel with the plus z raised to 4 by 4. So you have this this z with this z, that will form 2z. This z cube by 3 and this z cube by 3, that will have 2z cube by 3. So you have 2 by z, like this. Okay, and from this one can write this as 2 into 1 plus z square by 3 z raised to 4 by 5, like this. Okay. So one can write this series like this: 2 times sigma n equal to 0 to infinity z raised to 2n by 2n plus 1, sigma n equal to 0 to infinity z raised to 2n minus integral minus 1 2 plus 1 pnx square dx on the right hand side. And here we compare the coefficient of z raised to 2n. We are comparing the coefficient z raised to 2n, so both sides have summations. Okay, summation is there. We compare the coefficient of z raised to 2n. As we compare, you will be getting this. What is it? You will be getting, so you will be if we compare, you will be getting this. This expression integral minus 1 to plus 1 pnx square dx equal to 2 by 2n plus 1. Now by combining equations 4 and 3, we get 4 and 3. So the first part and the second part. This is first part, and the second part we are combining using this Kronecker delta mn. You know, delta mn, this is 1 when m equal to n. It is 0 when m not equal to n. That we know, that we have seen. So combining this, you have this. So if n and m are different, right hand side will be 0. And if n and m are same, you will get the required results. Okay, so we have the orthogonality relation for the Legendre polynomial.